So what's actually pretty cool here is if you do this vertically, really you're not doing anything except just moving where the datum is, where the general point is, and you end up with the exact same equations, just in terms of y. But one of the things that this does get us into is the idea of talking about energy. So, I think we've talked about the energy in a spring as being 1/2 ks squared, or kx squared, however you want to do it. So if we just think about, the spring being here, it has a, let's not do it up and down, let's do it lefty righty. If we have a spring, we'll call this the distance here. It has a potential energy of 1/2 ks squared, but it also has a kinetic energy of 1/2 mv squared, right? Because it's moving. Does that make sense? So if it's going, and so at any given point, this thing has a 1/2 ks squared plus a 1/2 mv squared for its total energy. This is not if it's going up and down, because then you also deal with a vertical potential, gravitational potential energy. But right now, the potential energy at any given point is total energy is potential plus kinetic, so 1/2 ks squared plus 1/2 mv squared. Well, what I did a second ago is, remember, I took the second derivative of the position vector, or the position equation, and the turned out to be, let's go find it. Okay, so let's see, energy, total energy. So we have 1/2 kx squared and then, so that's 1/2 kx squared, and this is potential energies, and then we're going to have 1/2 mv squared, which is its kinetic energy. Okay, so I have 1/2, and then the negative becomes positive, a omega sine this. Okay, all right. But now remember that omega is that k over, omega is the square root of k over m. Okay, so omega is the square root of k over m, so omega squared is going to be k over m. Okay? Oh, I forgot my m. 1/2 m, and then this is v squared. Let me rewrite that. 1/2 m, and then v squared. Okay. So I have a 1/2 on everything, and an a squared on everything. And I have a k cosine squared this, and then I have a omega squared, which is k over m, times m. Oh, that's going to be really nice. So I have m times k over m times sine squared omega t plus phi. So that's these guys right here. This is that. And let's see what else happens. The m's cancel out, and so the k's can come out. So I've got 1/2 a squared k times cosine squared of something plus sine squared of something. And that should be making something going off in your lizard brain of like something important's happening here, because you know that cosine squared theta plus sine squared theta is always 1. So this actually goes away. So the total energy of a spring, and I'm going to specifically write of a horizontal. Wow, that's having a lot of fun there, isn't it? horizontal spring. Horizontal spring is simply 1/2 a squared times k. So it doesn't even matter what the mass of the spring is that ends up getting thrown out in the wash. It really has to do with how far do you pull it in the first place times the spring constant. Which is pretty awesome if you think about it. Now, did we miss something where we talked about what A actually is? A. Oh, yeah, A is just how far out you pull it in the first place. Yeah, which makes sense because if I maximize this at 1, x at the max is A. So what's the max is however far you pull it out to begin with. So that's your maximum displacement is just A. So that's pretty cool, right? And then this is just going to be, the phi is going to be a representative of the phase shift, which is how much it's going to be off from that sine and cosine thing. And I think you can just find that out mathematically. So anyway, this is like kind of super cool and really kind of fun, and a neat idea is that the total energy is, oops, that's potential, that the total energy, and I think that your stuff does it down here, total energy, there we go, is just the 1/2 k times a squared. So that's pretty neat. So the total mass on the spring is just going to be right about there.